Hello everyone. In this session, we will discuss about how to handle the signed multiplication. So in the previous session, we have seen unsigned multiplication, and if the cases are going to be like this, if it is going to be a positive multiplier, then we can easily perform multiplication. Whereas if it is a negative multiplier and positive multiplicand, you can shuffle the sign of these two operands and then proceed in the normal fashion. Whereas if both the operands are going to be negative, then we will not be able to handle it properly with the normal multiplication. So in order to handle the signed process, signed operands, we are just going to make use of this Booth recommendation. So Booth is a famous scientist who has introduced a Booth algorithm to handle the negative multiplier. So if the multiplier is going to be negative, then we will be following the Booth multiplication. Okay. Now how to encode this multiplier? So if the multiplier is going to be negative, we will make use of this Booth algorithm and Booth encoding technique. So we are going to examine the bits of the multiplier in the pair by pair fashion. If it is going to be 0, 0, you are just going to replace it with 0. That means you have to multiply the multiplicand with 0. If the bit pattern is 0, 1, then you have to multiply with plus 1. If the bit pattern is 1, 0, minus 1, 1, 1, it is 0 into m. Okay, maybe we will just examine this for the negative multiplier. So if the multiplier is minus 3, the binary equivalent first you have to write it. So for minus 3, the binary equivalent is 1, 1, 0, 1. Okay, now we have to do the Booth encoding. So for Booth encoding, the pairs, the bits of the multiplier are going to be examined in the pair by pair fashion. Okay, when the last bit LSB is going to be considered as I, then we have to compare with I minus 1th bit. Actually, we don't have any I minus 1th bit, so we have to pad with 0 here, and then this pair has to be examined. And then when you are going to examine this bit I, then this will become I minus 1. So we will be examining this 0 and 1. So these two these two bits will be compared. And when this is going to be ith bit, this is I minus 1th bit. So we will be looking into these two pairs. Then when this is going to be I, this is going to be I minus 1. So we will be examining these two pairs. So the bits of the multiplier are going to be examined pair by pair starting from the LSB. This is considered as ith bit. So you frame one 0, always add one 0 and consider that as 9 minus 1th bit. Then you start encoding. Now how you will encode for minus 3? It is going to be 1, 1, 0, 1. So to encode this, okay, I will just add one 0 here. So that is 1, 0. 1, 0 means it is minus 1. So you have to encode it as minus 1. For 0, 1, okay, when I want to encode for 0th bit, that is 0, 1. For 0, 1, it should be plus 1. So I will be encoding it as plus 1. And for 1, 0, 1, 0, it is going to be minus 1. And for 1, 1, it is 0. Okay. So whenever we find a negative multiplier, first write the binary equivalent of that multiplier. Because it is a negative number, you write the 2's complement of that number. And having written this 2's complement of this number, apply Booth encoding and form the Booth multiplier. When this Booth multiplier is performed, then we can proceed with the normal multiplication. Now we will just see how to perform the multiplication for this case. Maybe I will just continue for this example. It is plus 13 multiplied with minus 6. 6 here we are having a negative multiplier. Whenever we find the negative multiplier, apply Booth encoding and then start the normal multiplication. So plus 13. So plus 13, it is going to be the multiplicand, a positive number. So you are going to represent in the normal binary representation. So the binary equivalent of plus 13 is 13 magnitude is 1, 1, 0, 1. Of course, the magnitude itself is 4 bits. Then we will be representing the sign bit with 1, 0 here. So it is going to be 0, 1, 1, 0, 1. And now the second operand is minus 6. So of course, first we will write it for plus 6 in the 5-bit representation. Then we will write for minus 6. Okay. So the plus 6 is 1, 1, 0. Okay. And because we are representing in 5 bits, we will be representing it as 2 zeros. This is going to be the 5-bit representation of plus 6. Now for minus 6, take 2's complement. So 0, 1. This one will become 0, 1, 1. So this is going to be the 2's complement representation of minus 6. So I will write minus 6 here. Okay. So plus 13 has to be multiplied with minus 6. It is nothing but 1, 1, 0, 1, 0. So we have to multiply these two. As I already told, the doing the multiplication in the normal method is not possible. So we are trying to do with the help of the Booth algorithm. So Booth encoding has to be applied on minus 6. So how you will be encoding this Booth concept on minus 6? Okay. Now you have to examine the bits in the pair by pair fashion. So first we are going to see for 0. So for 0, you have to form a pair. So you'll be adding one 0 extra here. So 0, 0, 0, 0 means it is going to be 0. Then 1, 0, 1, 0 means minus 1. Okay. Then 0, 1. So for 0, 1, it is going to be plus 1. And then again 1, 0. So this pair 1, 0. For 1, 0, it is going to be minus 1. And then you have 1, 1. So for 1, 1, it is going to be 0. So the Booth encoded format for minus 6 is 0, minus 1, plus 1, minus 1, 0. So that's what written here, 0, minus 1, plus 1, minus 1, 0. Now for performing this multiplication, you write the multiplicand as such in the binary representation, and if it is a negative multiplier, find the 2's complement representation of that number, then form Booth encoding. Having done this, we can just normally proceed with the multiplication. Now we will just see how this multiplication is going to be carried out. So again I will repeat, for plus 13, the number that is to be written is 0, 1, 1, 0, 1. Okay. And then for minus 6, we have applied Booth encoding, and this number has to be written. So it is going to be 0, then here minus 1, then here plus 1, then minus 1 and 0. So now we have to perform multiplication on these two operands. How is that we are going to do? Okay, so when you multiply, you examine this bit. Okay, it is 0. So if you have 0, then the partial product is also going to be 0. And here we have 5 bits. So whenever we have 5 bits, we know that the partial product the length will be twice the length of the multiplicand or multiplier. The whichever is maximum, that will be considered here. So since we have 5-bit multiplicand, we will write it as a 10-bit partial product. So the 10-bit partial product will be 0, 0, 0, 0, 0. So 5 bits to represent this, and 5 more bits extra. 1, 2, 3, 4, 5. So when you are performing this multiplication of n-bit number, we are going to write the partial product as a 10-bit number. So this is going to be the partial product 1. Then examine the next bit. So the next bit is minus 1. So we have to multiply this number. Please listen. We have to multiply plus 13 with minus 1. So when you are multiplying plus 13 with minus 1, the answer will be minus 13. So what is the binary equivalent of minus 13? So you have to take 2's complement of plus 13. So 2's complement of plus 13 will be equal to, so you will take this number, it is 1, 1, 0, 0, 1. So you have to take 2's complement of plus 13, so it is 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So this is going to be the binary equivalent of minus 13. Now when you multiply this multiplicand with minus 1, the partial product will be negative, and it is going to be this number. So you have to write down this number, and you are doing this for this second bit. So this will be you will not write, you will not write from this bit. So you have to examine, and you have to start writing from this bit. So the answer will be 1, 1. Then this is 0, 0, 1. Okay. Now we have to extend the extra bits. As I already told, for sign bit extension, whatever is the MSB, so this is going to be the sign bit. This only has to be extended. So we will be writing this one here this many times. So 10 bits representation you have to do. Okay. Now coming to the next number. So you have done with this. Okay. You are done with this. Now you will start for the third bit. Third bit is plus 1. So you will be getting the same answer. So whatever you have written in the multiplicand, that will be copied as such. So it will be 1, 0, 1, 1, 0. Then all the remaining bits should be copied with the sign bit. So the sign bit is 0. So you will be having 0, 0, 0. So this is going to be my partial product 2 for the second bit, and this is going to be partial product 3 for the third bit. Of course, we have 5-bit multiplier, so we have to write 5 partial products. Okay. Now we would start for this minus 1. Of course, we have to examine for this. So 3 bits have been already done. So you have to start from the fourth bit. So you are multiplying with minus 1. So whenever the multiplicand is multiplied with minus 1, you will be getting the negative partial product. So this is going to be the partial product. We have to write the 2's complement of plus 13, which we have already done for PP2. So whatever we have written for PP2, that we can copy here. So this is going to be 1, 1, okay, then 0, 0, 1, and then the extra bits has to be extended with the sign bit. So the sign bit will be extended, and it will be written as 1, 1. Okay. So this is going to be the partial product 4. Now we have to write the partial product 5. So fifth bit, it is going to be 0. So 4 bits already done. For the fifth bit only we are writing. So for fifth bit, you have to start writing from the fifth position. So when you multiplicand with 0, it will be 0. So the partial product will be 0. So you will be writing 0 as such. So now we have written all the 5 partial products. There are 5 bits in the multiplier. So you will be having 5 bits in the 5 partial products. Having written all these partial products, now we have to find the sum of all these partial products to get the final answer. Okay, now we are going to do this addition. Of course, it is 0 added with the don't care, so it will be 0. Then 0 plus 1, it is going to be 1. 1 plus 1, it is 2. 2 means 1 0. So 0. Then you will take a carry here. Okay. So this is going to be the carry. So 1 plus 1, 2. Again 1 0. So you will be writing 0 here. And then you will be taking the carry to the next bit. So please listen how am I doing this addition. So you just please count it in the decimal. And when you are writing the answer, you convert into binary. So 1 plus 1, 2. 2 plus 1, 3. So for 3, the binary representation is 1 1. So write the 1 and the LSB here and take the MSB to the next digit. Okay, it is 1. Now you please listen, 1 plus 1 2, 2 plus 1 3, again the same thing. So you will be having this 1 here and then you take the next one to the next bit. Okay, now 1 plus 1 2, it is 1 0 0 1. Okay, now 1 plus 1 2, 2 plus 1 3, it is 1 1, so it is 1 1. Okay, 1 plus 1 2, 2 plus 1 3, so 3 means 1, then you will add a 1 here. 1 plus 1 2, 2 plus 1 3, so again it is 1 1, so you will be writing 1 1 and excess 1 will be taken here and it's removed. And suppose for example when you are adding this numbers like this and when you encounter a number like 5, okay, now what is the binary representation of 5? You will do this Dana division, 2 2s are 4, the remainder is 1. Okay, 1 2 is 2 0, so you will be getting the number as 101. So if you get the number like this, then you will be writing this 1 here, and what is left over? 1 0. 1 0 is nothing but 2. So you have to take 2 to the next digit position. Okay, that's how you have to do the addition. When you are doing this addition, you can get any number like this. So you convert that into binary, write the LSB, and whatever is left over, the leftover number, you find the decimal equivalent and you take that number as a carry to the next digit. If you proceed like this, you won't make any mistake during the addition process. Hope it will be clear to everyone. Okay, now you have written the answer. This is going to be the final answer. Okay, how you will interpret the final answer? So this is an end around carry in 2's complement. You will be ignoring and you examine the first bit. The first bit is 1, so it is going to be a negative number, so you will put a minus sign for the result. Now to find the magnitude, the remaining bits you have to take the 2's complement of the given number. So the 2's complement of this number is 0 1, then it will be 1 1 0 0 1, then 0 0. So this is going to be the final answer. Okay, now what is the product of 13 plus 13 into minus 6? Okay, if you multiply, you have to get minus 78. Okay, now this is the answer you have got. So we have to check the magnitude for this. Okay, what is the magnitude for this? This is 2401. This is 2 2. 2 2 is 4. 2 3 is 8. 2 0, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. 2 6 is 64. Now we add all these numbers together. 8 plus 4, 12. 12 plus 2, 14. Then 14 plus 64, it is going to be 78. So if you add all these numbers, you will be getting 78. That is the magnitude. And already we have interpreted minus sign from the MSB. So the answer is minus 78. So when you multiply plus 13 with minus 6, so the answer plus 13 into minus 6, you have to get minus 78. So that's the answer you have already got here. So this is how you will be doing the Booth multiplication. So to quickly walk through on the concepts what we have discussed, if the multiplier is negative, okay, you will check the multiplicand sign. If the multiplicand is positive, then we can shuffle and proceed with the normal multiplication. Otherwise, in Booth encoding technique, it will be able to handle both positive and the negative multiplier. Whatever be the multiplier, if the multiplier is negative, then apply Booth encoding technique. And when you apply Booth encoding technique, you write the representation of that number in 2's complement form. Then examine the bits in the pair form. Okay, when you are examining, the last bit will be ith bit. So you have to add 1 0 and then form I minus 1. After encoding that into this Booth encoded format, then you will proceed with the multiplication. And when we are doing this multiplication, if it is a negative number, you will write the 2's complement of the multiplicand, 2's complement representation of the multiplicand. If it is positive one, you would write the number as such. And when you are writing, the sign bit has to be extended. So these 2 points have to be remembered when you are doing the Booth multiplication. So this completes the discussion of Booth algorithm, Booth implementation, sorry, not Booth algorithm, Booth implementation of negative multipliers. So in the next session, we will discuss about how this Booth algorithm works out and how it could be implemented, what is the hardware details, everything we will discuss in the next session. Thank you.